introduces lab to motion of a falling object. The purpose of this lab is to investigate the motion of a falling object by applying Newton's second law and the momentum principle, both with and without the effects of drag. A brief spoiler of the results, where the computational model with drag force was obviously more closer towards the experimental model. Here are the formulas that we are going to use in this lab. Newton's second law, which is F equals ma. Velocity update formula, which is V final equals V initial plus F net over m times delta t. Position update formula, where R final equals R initial plus velocity times delta t. And force of gravity, where F gravity equals negative mg times j hat. And force of drag, which is F drag equals negative b v squared v hat. Alright, so some main physics principles are Newton's second law, which relates force, mass, and acceleration as I showed you earlier, and the concept of gravitational force. It also examines drag force, which opposes motion and is influenced by the object's speed. Some key assumptions that were made during this lab include that the motion occurs solely along the y-axis. The drag force is always proportional to the square of the velocity, and the force of gravity remains constant throughout the experiment. Here are the initial conditions in the lab. The system is a Rubik's Cube. The surroundings are tables, hands, air, and anything else that affected the motion of the cube. Initial position vector is 0, negative 0.018, 0 meters. Initial velocity is 0, 0 meters per second. The mass is 0.0846 kilograms, and j hat is 0, 1, 0. This is the video that was taken and then was analyzed through the software called Tracker. This is the data that was analyzed through Tracker. This is a computational model that only took gravity into account for net force. Okay, so this is the code for it. I changed the mass to 0.0846 and then the initial position to 0, negative 0.018, 0. And then I changed the fnet. I changed fnet to negative ball.m times g times j hat, which is equivalent to the gravity force. And because there is no drag force into this one, that's the net force. And I used the velocity update formula in ball.well equals ball.well plus fnet or ball.m times delta t, and the position update formula below that. This is the computational model that took gravity and drag into account for net force. So this is the code for it, and I kept everything pretty similar to the last code I showed you guys, but the only thing I changed is that b is not 0 in this case. It's 0.028, which I got through trial and error, and then I used that to get f drag, and I added that and fg together to get net force. Okay, so some similarities and differences between the two computational models are that they both calculate the gravitational force and use it to determine the net force. The key difference is that one model incorporates drag into the net force calculation while the other considers only gravity. As you can see, the computational model with the gravity and drag force is closer to the experimental model because it takes drag force into account for the net force, but computational model with gravity doesn't. Alright, since the results showed that the computational model with drag was more aligned with the actual experiment compared to the model without drag, we can conclude that there was no significant error in the underlying physics. However, there are some other errors that were possible, which includes human inaccuracies during the experiment and the possibility that the value of drag coefficient b may be slightly imperfect. So what does it mean? Terminal velocity is reached when the drag force becomes equal and opposite to the gravitational force. Only the model that includes a drag predicts a terminal velocity. This is reflected in the graph where the curve flattens and becomes linear, indicating a constant velocity after the force is balanced. What if? The terminal velocity remains the same as it only depends on the speed required to produce a drag force, equal and opposite to the object's weight. Therefore, the starting velocity is irrelevant in determining terminal velocity. Alright, thank you all for listening. Have a nice day.